Good evening,
Yeah,
sir.
I hope everybody is doing well. So last class we started with magnetism, moving charges and magnetism. So that chapter is what we are under process. So I have covered almost 50% of it. So we are left with 50%. I also gave few questions for practice. So I hope you guys have positively tried. Some questions, the concepts still I have not taught. So that even if you try, you might be facing difficulty. No worries. Okay, those concepts I'm going to cover in this today's lecture. So we'll finish it and then we will go back to those concepts also. I mean, those problems we will try to solve it. Okay. So now we are continuing from where we left off in the last class. One go on. Yeah, it is on my right hand side. I hope. Yeah, it is initialized. You can see here, these are the questions that we have solved. In the last lecture, we tried to find out what is the force experienced by a charged particle. So whenever a figure is given, just you have a single wire that is carrying a current of 4 amperes. You wish to find out what is the force experienced by that corresponding current carrying conductor at a distance of zero point 0.2 meters from it. So a radial distance. So here again, this formula is very important. So again, we make use of the formula D is equal to mu naught I upon 2 pi A. So we make use of this. Now, to find out magnetic field, this you use it and you find out as 4 microtesla. Then you apply the formula for force. F is equal to q v b sine theta. Why we are using this formula? That is because whenever you have a particle that is trying to move in the presence of magnetic field, then charge of the particle is given by q. The velocity with which it is moving is v, and the magnetic field that it is experiencing is b. So you will use qvb sine theta. So this is the formula for all the particles in motion in magnetic field. This you have to keep it in mind. Okay, force experienced due to magnetic field. That is what FB I have used. B is for magnetic field. Same way we have learned FE also. Force experienced by a particle due to electric field. Right? So F is that is Q into E. Charge multiplied by electric field. So we are just having a small recap of what we learned in the last class. So now we will continue with the other concepts and then we'll go back to the questions. Okay. So we'll see, children. We are going to the next topic for the day. So let me just write it. So now the topic for today is basically we are going to see what is the magnetic force experienced by a wire that is carrying current. Okay, so wire that is carrying current in in two directions as well as in the same directions. Two wires we are taking. We try to find out what is the force experienced by that corresponding conductor. So let us see. There are different cases here. So let me first put the heading. We will see what is the force on a small current carrying wire force on a small current carrying wire due to infinite large current carrying conductor. Due to an infinite large current carrying conductor. We will see this. What is the force experienced by it? Okay. So the reference figure I'll draw it. So this is how the reference figure looks like. So I'm taking a conductor that is carrying current. So a straight conductor children I'm drawing it. So say the amount of current that is flowing is I. We are generalizing now. Okay. So the current flowing in this conductor is I. Okay. It's carrying a current of I amperes. Now, if I'm going to take another conductor, okay, away from this conductor. So this conductor is my reference conductor. Let me mark it as AB. Okay. So this AB is of infinite length. Okay. So it is a large conductor. Okay. So dot dot dot, it is of infinite length. Okay. It is extending on both the directions. Infinitely it is extending. Say positive infinity, negative infinity. Now when I'm taking another conductor, say another straight conductor at some distance. So let me draw that also. This is another conductor. The current flowing in this conductor Let me call it I dash. Okay, I'm trying to generalize. So if there is another conductor present at a distance of a units, small a, from an infinitely long conductor carrying current, then what is the magnetic field or the magnetic force? Okay, not field. What is the magnetic force experienced by that corresponding conductor is what we are going to find out. That is the relation is what we are going to write. Okay. So whenever you have a long infinite current carrying conductor, so this is the long infinite current carrying conductor, and this is the secondary conductor. So the first conductor will act as your primary. So I will call this primary conductor. And the next conductor, the second wire which is present, we will call it secondary. Okay. So this is the secondary wire or secondary conductor we can call it. Okay. Secondary wire which is carrying the current of I dash, which is present at a distance of A. So what is the force on the small current carrying conductor is what we wish to find out. So the force is given by the expression. Whenever you have cases like this, the force experienced F is given by mu naught times current I, because you are trying to find out. It is given by mu naught. Mu naught, you know, it is a constant. Mu naught times current that is flowing in your conductor, that is your infinite conductor. Say it is I upon 2 pi A into then your secondary conductor, which is having a current of I dash, so into I dash times your length of your secondary conductor. Secondary conductor will be is not infinite here; it is just of finite length. So into its length L. So this is the formula to find out what is the force experienced by a small current carrying wire which is placed at a finite distance from an infinite current carrying conductor. Okay, so the length of this conductor is, say, I've given AB for the first one, we'll call this CD. Okay, so CD is nothing but L. We have generalized. The length of that small conductor is L. So therefore, the expression for the force experienced by a small conductor carrying current present at a distance of A from an infinitely long conductor carrying a current of I is given by this relation. F is equal to mu naught I upon 2 pi A times I dash into L. So you want to write it as a single expression. How can we write it? We can write it as mu naught I dash L upon 2 pi A. This is the force experience. Okay. So this formula is very important for us. So you can see that whenever you have two conductors present at a finite distance, you can find out what is the force experienced by the short conductor with respect to the long one. You can find it using this relation. Okay, I hope this part is clear. Okay, this is one case. This is the first case. Let me call this as case one. We have different cases for this. So let me call this as the first case. So I am writing it as case one. Okay. Now we are moving on to the next case. That is for the second case. What is case 2? We will see that. Okay, we will try to discuss it. Now, in the second case, no doubt, I am going to have a primary conductor which is of infinite length. So I am again redrawing the primary, conductor which is of infinite length. Okay. So here, say it is plus infinity, here it is minus infinity. It is extending, and it is carrying a current of, say, I. Okay, the current carrying conductor here of infinite length is I. It is carrying a current of I amperes. Okay, the length is infinite length. Now, now you have one more. Now you have the second conductor, which is your secondary conductor, which is not placed vertical but horizontal. Like this, I am placing the conductor like this now, and the current that it is carrying is I dash again. Okay, the length is also L only, as we took for the previous case. The length is L only. Now we wish to find out what is the force experienced by the small conductor again due to this large conductor that is carrying current. Again, here also we have the distance between both of them as A. The distance is A. Okay. The conductor, the secondary conductor to the primary conductor, the distance is just small a units. And the secondary conductor is of finite length. Primary conductor is of infinite length. Now, what is the difference between these two figures, the first figure and the second figure? The difference is only the orientation. In the first figure, you can see both are parallel to each other. The second figure, they are perpendicular to each other. If you're going to extend the line of action of the secondary conductor, you can see it makes an angle of 90, right, with the primary. That's all. The orientation only has changed. Okay, all the other things remain same. If this is the case, then what is the expression for force? Whenever you have a conductor, so case 2 is, I'll just write it here because you can easily try to differentiate between the two. The second case is when the small conductor is kept horizontal, horizontal and is perpendicular to the primary conductor. Okay, this is the condition. Okay, this is the case 2. So now we are writing the expression for force. So we'll see how to write down now the expression for force. This is also quite simple. You should know the expression. So F is equal to, same way we will write mu naught. Again, it is the same thing, only certain things would change. Mu naught times both the currents in both the conductors. Infinite length conductor, current is I, times the short conductor, the current is I dash. Mu naught times I dash. Okay, upon 2 pi. Now we are not writing A here. That's all. This is what we are writing. Mu naught I dash upon 2 pi. That's it. And you have another term, the next term, which is ln. It is ln of A plus length. The length is of the short conductor is L. Small l I have taken. So A plus L upon A. This is the formula. Okay. When you have another conductor, which is perpendicular to your first conductor at a distance of A, and the current carrying is I dash, then the force experienced by the small conductor is given by this expression. Okay, here ln is not log, it is ln. Okay, it is ln. Okay, so we are using this expression. So like this, there are two different cases. Okay, these are the two major cases that can come from the competitive point of view. Now, I have seen some questions in some papers. There are some questions. Now, for JEE and all, if you see, there are certain questions where there are two conductors. Okay, two conductors are also infinite length. That is also possible. Okay, some papers, I have seen, so they ask questions like that also. There can be a case. Okay, so I will include that also here. Okay, so that is case 3, because we need to learn everything in detail. So one more case is there. Okay, this is a special case. First two are the basic ones. Now here, the third one, which I'm going to discuss, is a special case. So we will see this also. The third case is where you have two conductors. It is the force experienced by two infinite conductors. Okay. So now we are going to see the force experienced by two infinite conductors carrying currents. Carrying currents, say I and I dash. Okay. They are separated by distance of, say, A again. Okay. That's it. So we are taking again two conductors this time. So there are two conductors. Both are of infinite length. So they are extending above and below, positive and negative infinity. And the currents that they are experiencing, it is I and I dash. So the first one is I, the second one is I dash. Okay. So the distance between them is small a. We are taking like this. Now this is the case. Now if this is going to be the case, what is the force experienced by such conductors when there are two conductors that are carrying currents which are different, and they are having, a finite length or a distance between them. So in that case, so we try to find out what is the expression for the force. Okay. So you know that force, general expression, force is equal to BIL, BIL sine theta. So that you can write as BIL. Okay. I'm writing as BIL. The general expression. Now F, force acting per unit length, if I want to find, I will just rearrange this term. So you will get F upon L is equal to B into I. This is general, what I'm writing. So force acting per unit length is B times I, magnetic field times current passing through it. Okay. So therefore, now we go and apply the force per acting per unit length is equal to, we already know what is the expression for force of two conductors. Mu naught times current. It is the product of both the currents. First current is I, the second current is I dash upon 2 pi A. So we use this relationship. So this is the force acting per unit length when two conductors are going to carry currents, okay, and separated by distance of A units or R units, whatever it might be. So this is the relation for force acting per unit length. So you will make use of this. So now when you make use of this, you can solve the first question which I have given in the practice questions of moving charges and magnetism. So that is this concept only. So you make use of this, you will get the answer. Okay. So this is case 3. This is a question which is of a different kind. So like this, you have 3 different cases. Okay, case 1, case 2, and case 3. You can go through the notes. Okay, so it is very clear. So it's easy. Just you have to write down the formulas. So I again recommend, I've been repeating this for quite long, but again I'm telling you, it's better that you maintain a formula book, okay, for chapter wise, so that it's easy for you to have a recap. At the end of the day, you can have a recap and it will be useful for your exam point of view as well. Okay, so that's a small tip. So we are moving on. Next, Biot-Savart law already I have explained. Now we are going to see the applications of Biot-Savart law. Okay, so we are going to express Biot-Savart law. We are going to express it in terms of velocity. Okay, in terms of velocity of the particle. So we'll try to see how to express the Biot-Savart law in terms of velocity of a particle. Okay. So again, you know that Biot-Savart law gives you the relationship with the magnetic field experienced by a small portion of a random wire that is carrying current. So due to a point P, okay, away from it at a distance of r, at a displacement vector of r. So we all know that dB is equal to, you remember the formula? What is the formula for Biot-Savart law? Can anybody volunteer and tell me? dB is equal to mu naught upon 4 pi.
Mu naught by 4 pi into ideal sine theta.
Yeah, ideal sine theta. Okay. The theta is the angle. Okay. So based on that, here we are going to express Biot-Savart law in terms of the velocity. How do you write it? See, B is equal to mu naught by 4 pi is intact. We are not disturbing that constant term. Okay. Mu naught by 4 pi is intact. That ideal sine theta, that is where we are going to, do a substitution. We will express that in terms of the force itself. Okay. So we will write it as Q V sine theta upon r square. This is in terms of velocity. Theta is anyway the angle, no doubt about it. So here V term comes into picture. This is nothing but the velocity. And what is theta? Theta is the angle between your conductor and your between I and between R. Okay, the angle between I and R. That R is nothing but your displacement vector. You must keep in mind. Okay, so that is the angle theta. So this is the formula in terms of velocity for Biot-Savart law. So this formula is important. Okay, so this is one aspect of it. Okay, same way, if you can see, what are the ratios of force due to magnetic field and electric field? Okay, That is also one thing which you will have to note in this point. So ratios. The force experienced due to magnetic field, MF means magnetic field. I have also discussed using another representation. I hope you guys remember. I used FB representation, F suffix B. Force due to magnetic field and force due to electric field. Ratio. What is this ratio? What does this ratio ultimately give? Okay. That is also necessary for us. So when you try to find out the ratio for this, okay, so you will get a relationship that it is equal to v square upon c square, where v is nothing but the velocity, c is nothing but the speed constant. You will get a relationship like this when you try to substitute the force due to magnetic field, force due to electric field, and then when you try to simplify it, you will get the ratio as the squares of the velocity and square of the speed constant also. So these are the two things. And then when you go for rearranging for C term or C square term, you can find that C square is equal to 1 upon mu naught times epsilon. So this is one aspect where you know that epsilon naught is different and mu naught is different. Epsilon naught comes with respect to the electric fields and charges. Mu naught comes here in for moving charges and magnetism. So these are the two things. One is permittivity, one more is permeability. So there are two different things. Okay. So this is how the C square term comes into picture. These are the conditions. This is just the condition which you will have to keep in mind. Suppose they ask you the ratio, definitely velocity value will be given in the question. If that V is given, can't you find out the ratio? Directly you can find. V is given, you will substitute in the place of V. C, you already know the C value is a constant value. Speed constant, I do not tell, everybody will be knowing it. 3 times 10 power 8 meters per second. So whenever you have questions where they ask you the ratio of magnetic and electric field, direct substitution. You will substitute the value of velocity, and then C you already know, substitute, cancel out, and get it to the simplest ratio. Okay, that is why I have given this. Okay, this is the relationship. Right. So now we are moving on to the next part. What is the circular current loop as a magnetic dipole? So we will see that. What is circular current loop? We will see. That is the next concept which is coming. So we will now discuss. I'll scroll to the next page. We are going to discuss what is the circular, say, current loop as a magnetic dipole. Okay. How can we express it as a magnetic dipole? Here, whenever you have a circular loop which is carrying current, okay. Now loops, whenever I say loop, you know that loop is a circle like this. Here I have drawn a loop. The loop can carry current in two different configurations. Okay. One, it can carry current clockwise. This is one possibility. One more possibility, it can carry current anti-clockwise. That is also one possibility. So these are the two different possibilities for circular current carrying loop. Okay. So out of these two figures, say this is the first one and this is the second one. Two figures are there. So you can see the first one is carrying clockwise current, right? So this is clockwise. The second one is counterclockwise, or you can say anti-clockwise, ACW. So I'm using a short form. Okay. Now here we want to understand whenever you have a circular loop which is carrying current, be it clockwise or anti-clockwise, what polarity it gives? What is the polarity that it shows? Polarity in the sense, I am talking about the magnetic polarity. Whether it is going to represent a south polarity or whether it is going to represent a north polarity. Okay. So now here it is very simple. Based on the nature of the current, the direction of current, that is whether it is going to be clockwise or anti-clockwise, you can easily come to a conclusion. Okay. So always remember, clockwise current will always represent south polarity, okay, or south pole. Why south pole? The way you write the letter S, okay, the way the letter S is written. This is a shortcut trick to remember, okay, not a concept, this is a trick. The way letter S is written, you can see the arrow marks, the direction in which they are going to move. Okay, that is representing a south polarity. It is just a shortcut trick to remember. Same way, anti-clockwise is going to represent north pole. Again, the way the letter N is written, if you see the way letter N is written, it is written like this. So that is the reason it is representing north pole. It is a tip to identify based on the clockwise or counterclockwise current in a loop. You can identify what polarity it is, whether it is going to be a south polarity or whether it is going to be a north polarity. So always remember, clockwise means it is south, anti-clockwise means it is going to be north. Okay. Now, which rule gives us the information of this? Now here you have, uh, based on the direction of current. Okay, you can use your right hand thumb rule. Where you have the direction of current, you try to apply it. You can see that the magnetic lines of forces are curling, are going to curl. Okay, the way they are going to curl, again, that also is going to be in the direction either outward or it will be in the direction inward. So based on that, it is easy for us to identify whether it is going to be a south pole or whether it is going to be a north pole. So for south pole, always remember it is going to be a cross representation. I will use it. I will represent using a cross like this. For anti-clockwise, because it's north pole, I represent using a dot. Now, can anybody tell me what is the meaning of this cross and dot? What does cross represent and what does dot represent? Anybody? It is just with respect to magnetic field. Whether magnetic field is outside the plane of paper or inside the plane of paper. That's it. That is what is the cross and dot. Can anybody tell me? This is a simple thing only. Yes? Cross and dot in magnetic field. You can volunteer. It's okay even if you don't know. Just give it a try, no?
Sir, cross inside, sir.
Yes, cross will represent magnetic field inside the plane of paper. Okay. Now it is inside. Now you see how you identify it is inside. You can see that for clockwise current, left side the current is above. By the time it comes right, it is below. So you fix on to the left side as your reference. Hold that. Imagine that you're holding your current carrying conductor using your right hand. When you coil the four fingers, where are your four fingers? Index, middle finger, ring finger, little finger. Don't you think they are going inside the plane of paper first? That is why you represent using a cross. Now, when you come to anti-clockwise, you can see the arrow mark is outside. So when you're going to hold it, you can see the fingers curl and come outside the plane of paper. That is the reason it is a dot. Now, that is the scientific reason behind a cross and a dot, representation or a notation. Okay, that is how the cross and dot came into existence here. So, clockwise currents, apply your right hand thumb rule. You can see the fingers are going to curl and they are going to go inwards, inside the plane of paper. That is the reason it is cross. That's why I'm stressing on this. By the time for anti-clockwise, when you're going to apply, you can see the fingers curl out and they are facing you. That is the reason we are representing dot. So cross represents magnetic field perpendicular and inward to the plane of paper, and dot represents magnetic field perpendicular and outward the plane of paper. Okay, this is what is cross and dot representation. Okay, so now here I am just mentioning that cross represents magnetic field it is magnetic field. It is going to be inside and perpendicular, and dot represents the magnetic field outside and perpendicular of the plane of paper. So that is what is your cross and dot representation. Fine. So this is an important aspect for you guys to keep in mind. So now we have understood what is the cross and what is dot representation and what is the polarities also. We have come to an idea. Now, magnetic dipole. Coming to magnetic dipole part. Okay. Now, whenever you have a magnetic dipole, now what is meant by a dipole? Whenever there are two polarities, you call it a dipole. Electric dipole, you remember, right? There also you have two two charges, one positive and one negative charges. When you are separating them by distance, again the electric field due to them. So you can see it is going to, when you're going to join those two conductors, then you call that as a dipole, electric dipole we call it. Here, same aspect. Here also we call it as a magnetic dipole. So whenever you have a magnetic dipole, what is the magnetic moment associated with it? Okay. So when we try to understand that, the magnetic moment is given by a simple formula, capital N is equal to a current that is passing through it is given by, say, I, okay, I times the area of the current carrying loop. What is the area here? Because you have a circle which is carrying loop, so area is going to be pi r square. So I times pi r square, where r is nothing but the radius of your current carrying loop. Okay, this is the magnetic moment. Okay, simple. So this is all about it. Now, if there are n number of turns, now this loop is having only one turn. Not necessarily all the time it has to be a single loop. If you have many turns, n number of turns, then this formula becomes Ni into A. Okay, then the magnetic moment becomes Ni into A. Simple. Is it clear? So this is all about your magnetic moment. So what is the SI unit of magnetic moment? Current is amperes, area is meter square, so it is ampere meter square. Okay, because current is in amperes and area is in meter square. So ampere meter square, we represent it. Okay, simple. Yeah, so this is all about the magnetic moment and the polarities. We also understood cross and dot notations. So all that we have done so far. Next, we are trying to find out for an electron. If an electron is there and it is revolving, what is going to be its magnetic moment? So we will see that. Next, we will see the magnetic moment of a revolving electron. Magnetic moment of a revolving electron. If an electron is going to be revolving, what is the magnetic moment experienced by that electron? We try to find out in this case. Okay. Very simple. Again here, for that we need to understand what is the force experienced by the electron. Whenever there is the electron is going to move, so the force that is going to be experiencing, okay, is given by, so we can write it, the magnetic force in terms of velocity I'm writing. Okay. So V upon 2 pi r. Okay. So I'm expressing. So for a revolving electron, what is the force? This is the force it experiences, where V is the velocity of the revolving electron. R is nothing but the radius of revolution of the orbit. That is R. In this case, when you find out the magnetic moment M, you know M is equal to the product of currents minus the area. A here is the area. So again we are trying to express. So here current. If I am saying current, so here I am expressing that current in terms of the charge, the charge carried by the electron. So electron means the charge is E. So E times, we express as the product of the charge times the force that it is experiencing. Okay, so times pi r square. So we are going to express it like this. Okay, again further trying to express it, so it becomes E dr upon 2. So whenever you have a revolving electron, we can express it like this. Okay, here there is a change. Can anybody tell me what is the change here? How the EVR by 2 term came into picture? First one I told F. That itself is difference. Can anybody tell me what is F here? What did it say? Can we write force as V upon 2 pi r? Nobody noticed it. What is a force, children? General formula, F is equal to QVB sin theta. Yeah, QVB sin theta. One more thing, you can from Newton's law, MA. But how come we can write V upon 2 pi r? That too where V is velocity. Is it possible to write like this? It is different here. Nobody has noticed. See, You must be very vigilant. Force, this is F is not force here. Capital F is force, but small f here is actually the frequency. Okay. It is not the force, it is the frequency here. Fine. So nobody corrected. So small f here is actually the frequency. Frequency of revolution. Now you all know frequency is the reciprocal of time period, isn't it? Yeah. And you know distance traveled is equal to speed into time. Are you getting the connect now? Distance here traveled by the electron, circumferential distance. That is why we are taking as 2 pi r. When you are simplifying and go for a rearrangement, it will become b by 2 pi r. That is how it this came. Okay, so be vigilant. Fine. So even if I go wrong, you must be vigilant. You must correct. Okay. Yeah. So fine. So coming back. So here f is your frequency. Again, I'm correcting it. So frequency of revolution of the electron moving with velocity v and in the radius of the orbit is r. So frequency is v upon 2 pi r children. Then so that is magnetic moment is given by current times area. Current. Now we are trying to express that in terms of the charge and its frequency. So E into F. Then area is pi r squared. Then afterwards you go for the simplification. You know F is B upon 2 pi r. We are substituting it, and then going for the simplification, you will get EVR by 2. So this is the magnetic moment experienced by an electron that is revolving with velocity v and radius r. So final expression m is equal to EVR by 2. This is the expression. Okay, simple. Okay, so please be vigilant here afterwards. So this is about the magnetic moment. Fine. So now we are moving on. We are trying to next see what is the torque. Next concept we are moving on. Next is the torque. What is meant by torque? I hope you guys would have, heard about torque. Now somewhere or some point in your life. So what is torque? We'll see torque on a current carrying loop. Okay. We are going to see. Okay, what is meant by the torque? Simple. Torque, you have already learned this topic in grade 11, isn't it? So torque. When I say torque is nothing but it is the product of force and the perpendicular distance from the axis of rotation, right? That is what is a torque, isn't it? So real life applications where we come across torque, it can be opening and closing of your door. You can see when you open the door, the axis of rotation is nothing but your positive y-axis, and you are applying the force. And how you are applying? You are applying such that it is at an angle of 90 degrees, right, from the axis of rotation at a distance r. That's why we use the formula Fr sin theta, right? Or you can say it is a cross product also, right? So that is how torque comes into picture. Okay. So when you see the angle is 90, maximum, the torque will be maximum, and it is more efficient for us to do the work. Okay. Even spanner, when you try to tighten a nut using a spanner, okay, or you want to tighten a bolt using a spanner, how you are applying the force? The force is applied perpendicular. Why perpendicular? Why not at any other angle? Because at that angle it is easy. It is the torque that is going to be experienced is going to be maximum. When I say F into R into sine theta, the sine theta, theta value, when it is maximum, it is going to be maximum when it is going to be 90. That is the reason it is at an angle of 90. Okay. So this is how you identify what is the torque, what is the concept of torque, basic concept. Okay. So now we are moving on. Here we are writing the expression for torque. Okay. So tau is equal to, we represent torque using the Greek alphabet tau. So tau is equal to the cross product of magnetic dipole times magnetic field, M cross B. So we are using this particular relationship. Yeah, coming back. So torque is represented as the cross product of the magnetic moment and magnetic field, M cross B. So how we will write this? You all know A cross B is AB sin theta. Here it is going to be MB into sin theta. We express like this. Okay. So MB times sine theta. This also has another formula, children, which is BINA times sine theta. So what is here? What I have done? I have expressed for magnetic moment. You know, magnetic moment is NIA, right? So I am writing as BINA sine theta. Simple. Okay. This is the expression for torque. Okay. Keep this in mind. Torque experienced by a current carrying loop. Okay. In magnetic dipole. This is the formula that you need to keep in mind. Fine. So now we are moving on. What is the magnetic potential energy? So moving on to the next one. Magnetic potential. Magnetic potential energy stored in magnetic dipole. What is the magnetic potential energy that is being stored in a magnetic dipole? Here it is given by the relation wherein U is equal to, so we are using that relationship. So U is the representation for your magnetic potential energy. So U is equal to minus M into B times cos theta. So here what does M represent? M represents the magnetic dipole, and B is nothing but your magnetic field. Okay. So your magnetic moment and your magnetic field. Simple. So, and theta. Theta is nothing but obviously the angle between them. Okay, angle between M and B. So this is how you represent it. Okay. Here it is when I just write MB times cos theta. Here you need to understand that why we are taking the negative sign convention. Okay. So the negative sign convention is always used. Okay. This is based on the magnetic lines of forces. Whenever you say the stored potential energy in the magnetic dipole, you know the magnetic lines of forces always emerge from north and they converge at south, all those things you know. So here it is the other way around. It is the opposite. Okay. So that's the reason we take the negative sign convention. So now sign convention, the work done here is negative. That is why it comes as negative as per work energy theorem. Fine. So that's why we take minus sign convention. So minus mb times cos theta. Again, you substitute the value for magnetic moment. You will get it as minus BINA cos theta. That is the expression you will get for the magnetic potential energy. Okay. That's it. So then you can also write down what is the expression for time period. So how do you write the expression for time period? T is equal to, this is also a simple formula. T is equal to 2 pi under root I upon NB. So this is the formula for time period. Okay. So you can find out using this particular relationship. Okay. So like this, we can write down. Here, it is very important for us to note that I is basically your moment of inertia. The I which I have used here, capital I. Okay. It is not the current wala I. It's not the current I. It is moment of inertia. In terms of moment of inertia, we are expressing it. Okay. M is magnetic moment as usual, and B is nothing but your magnetic field. Okay. So therefore we are using this relation to find out what is the time period. Okay. So this is one aspect. Right. So like this, there are certain things that you will have to keep it in mind for the magnetic potential energy and correspondingly the time period also. These are the two relationships that needs to be known here in this case. Okay. Same way, now coming out, we have almost covered, okay, 90% we have done. And then coming to the last topic, which is going to be your moving coil galvanometer. So there is one topic left, which is the moving coil galvanometer. So we will see that also. What is meant by a moving coil galvanometer? Okay, what is a moving coil galvanometer? This moving coil galvanometer is consisting of an iron core, okay, which is in the shape of a cylinder, and you can see that there are so many windings, okay, of copper wire, fine insulated copper wire that is wound around it. Okay, it is placed, using a needle tip which is used to balance it, and there is a radial magnetic field that is provided to the coil from both the sides. Radial means it is going to be circular. Magnetic field is going to be from in all directions. It is circular. That's the reason we call it radial magnetic field. Okay. Now you can see the galvanometer is also a simple instrument which is used in the laboratory. In the physics laboratory, we use it. Why do we use a galvanometer? We use it for finding out the current in a circuit. If whether there is a current or not the value of current, whether there is a presence of current or not. For that only we use it. We use the galvanometer. Okay, that is a primary use to identify the direction of current and its presence. Only we use a galvanometer. It will show us the deflection. Okay, you can see initially the needle will be straight. It will be pointing towards the zero. And whenever you connect in the circuit and switch it on, when current flows, it will show a deflection. It will show what is the deflection for the amount of current that is flowing. Okay, the number of deflections per ampere it will show. So that is what is the moving coil. That is what is the galvanometer in general. Now that every galvanometer has got a setup inside, which is very similar to a moving coil galvanometer. Okay, so that is what we try to understand here. Now the coil moves. Now how the coil moves? You know that the coil is present and it is balanced on a corresponding tip. There is a spring mechanism that is provided. Now, whenever there is a current supply to the coil, you know that when current flows to the coil, what is going to happen? And provided that it is placed in magnetic field, you know that due to the Fleming's rule, okay, Fleming's left hand rule, there is going to be a force experienced by the conductor. I repeat, whenever there is a insulated, copper wire which is present around a soft core, soft iron core, and when it is placed in magnetic field, provided current is flowing through it, it experiences a force. This is due to the Fleming's left hand rule. When it experiences a force, because this coil, is present, the coil is wound like this. So therefore, by the time the current is going to reach the opposite directions, now the force is going to be experienced by the both the tips. Okay. So say if I'm going to choose 2 points, X and Y, I am taking a coil. This coil will have a many number of turns, n number of turns. Okay. I am just taking for one turn and I'm explaining. When you're placing it in magnetic field, the two radial magnetic field, now these 2 points will experience a force. One point will experience an upward force, wherein the other point will experience a downward force due to the relative direction of current. So when these two forces are equal and opposite, then the coil begins to rotate. So it rotates due to the torque that it is going to experience. So there is a torque children. Once it starts to rotate, now coil does not rotate forever. That is why there is a small spring that is kept. It is wound to a spring and there is a spring also which is being kept children. So when there is a spring mechanism, the spring is going to provide a restoring torque. Applied torque is due to Fleming's left hand rule. It rotates, but the spring will get twisted. The number of, it will twist and then it will stop the coil from rotating further. So therefore, your moving coil galvanometer can move and show the deflection in the pointer needle. So that is how it generally works. Okay, so this is the basic idea of a moving coil galvanometer. Okay, simple. So you need to just understand what is this device. Okay, so now when you are going to apply some voltage, okay, so then we try to understand what is the voltage sensitivity of the moving coil galvanometer. It is given by the symbol Vs. This is your voltage sensitivity. It is a highly sensitive device. Okay, so the voltage sensitivity of a moving coil galvanometer is given by a relation. We can say it is proportional to the number of turns upon resistance, N upon R. Okay, the number of turns per the resistance of the coil. So this is the voltage sensitivity of the moving coil galvanometer. Okay, so as I said, here you are going to have a coil. So there is a coil. So I'll show you. So we have a coil. Now to this coil, there is copper wire that has been wound. So there are so many turns of copper wire that has been wound to this like this. It is wound. Okay. When it has been wound and it has been placed between permanent magnets like this, two permanent magnets are there which provide the magnetic field. Say this left side is north pole, the right side is south pole. So the way it is being present, you can see it is curved. So therefore, all the magnetic, field lines would be pointed out radially like this. So they are pointed out like this, radially. Here also it is pointed out and it is present radial. So that's why we call this as radial magnetic field. Okay. So if this is the case, now this coil is being fixed at this end. So there is a point. So at this end, and then it is being connected to a pointer. Pointer is what shows the readings. Real time, it will show the readings. So this is the pointer, and on the top you will have a scale. There is a scale here on the top, like this. There is a scale. The center it will be zero. Usually the needle will be in the center. Now it is deflected. Okay, like this there are scales, children. Like this there are scales. So it is here. Now it is deflected. Why it is deflecting? Due to the torque that is being produced, it is deflecting. Now we write the expression for torque. You all know that torque is given by the letter tau. What is the formula? You all know that tau is going to be equal to m into b. Okay, right? mb sine theta. Now here, because of the radial magnetic field, you can see with respect to the coil in the number of turns, it is going to be at an acting at a perfect angle of 90 whenever there. That is why it is present like this. They have cut it in this shape and they have kept it. So the angle is going to be perfectly 90 due to the radial magnetic field with respect to the coil. So therefore, sine theta becomes 90. That term is going. I'm not writing that term because it is sine 90 is 1. So tau is equal to mb. Number of turns, you can see there are so many turns in the coil. So I'm generalizing. So we can get as BINA. So the torque you will get it as BINA. Now in this, if you see, okay, in this if you can see this particular value, okay, now is going to be represented as tau is equal to BIN into A, where I is your current passing through it, N is number of turns, A is area, and B is magnetic field. Okay, B is magnetic field. Now we can also express this. I'm marking it as equation 1. Okay, this is equation. Now I told you that there is a spring also present. Behind this, there is a spring. Okay, there is a spring that has been embedded. Now the spring is also going to experience the torque. Okay, when the coil rotates, the spring is also going to experience. It will try to restore the torque. So that is there is a restoring torque that the spring is going to provide. So I am going to write that as tau spring. It is given by the formula C into theta, where C is called the torsional constant of the spring. Okay, it is called the torsional constant, torsional spring constant. Okay, we call it like that. Okay, so whenever there is torque, due to the torque, the coil starts to rotate. At the same time, the spring will try to oppose the torque which has been produced. So it will try to restore the pointer to its normal configuration. Okay, this is what happens real time. So therefore, both the torques are going to be equal and they're going to be acting in opposite direction. So we try to equate both of them. Okay. So we try to equate them. So when you try to equate both the expressions, first one I'm calling it as 1, this I will call it as 2. So the restoring torque of the spring and your coil is equal. So we try to equate both of them. So when you equate, finally you can find out theta as BIN into A upon C. Okay. This is what you will get. This is the relationship for theta, the deflection. You can find out the deflection using this formula. How much is the deflection? We can find out using this relation. Okay. Same way, now we can write what is current sensitivity. Current. Current sensitivity is defined as the number of deflections per unit current. Okay. The number of deflections already I have given you the relation there. So go substitute, you will get B N A upon C, where C is your constant. This is current sensitivity. Okay, BAN upon C. Same way, voltage sensitivity. You know, from Ohm's law, you know V is equal to I upon R, right? So you can write I times upon R. So again, go to substitute children. Here you're going to get current sensitivity. I here is nothing but the current only. So IS upon R. So you will get BAN or NBA, anyways you can write, upon C into R. So you will get it like this. Now already we know BAN by C is nothing but theta, isn't it? So we can write it as theta. So it is nothing but theta upon V. The number of deflections per unit voltage. So you call this as voltage sensitivity. The above one is current sensitivity of the moving coil galvanometer. Okay, so these are the things that you will have to understand. So the important things. So now we have learned all the formulas and the underlying concepts, basic things we have seen, everything, all the formulas and certain areas I have also given you the special cases. Okay, so now we are going to move on positively. We will see what are the different cases based on which questions can be asked in this particular chapter. That is what we are going to see. Okay, so we will see that. Okay, so first one. So what are the different aspects we are going to see? So I'll discuss all of them with you. Okay, so there are certain things that you will have to keep in mind. Okay, so what are the different things? First thing, we'll try to visualize. Okay, I'll call this as the visualization. Okay, we try to visualize different cases. So say it is the first visualization. Visualization one. This is very important for your competitive approach. Whenever we do the competitive, when you do the exams, there are different cases or different visualizations that you will have to picturize in your mind before you start solving the problems. This is very important. When you read a question, you understand what is going on there. Once you understand it, the approach becomes even more easy. Okay, so that is what I'm going to now teach. So first visualization. Say, if an electron is not deflected, okay, and when it's passing through a particular region in space, okay, I'll write it here. If an electron is not deflected, if an electron is not deflected in passing, okay, in passing through a certain region in space, okay, in space. Now I'm asking a question. Can we be sure or can we be certain? Okay, can we be sure that there is no magnetic field, that there is no magnetic field in that region? This is one visualization part which you will have to know. The thing is how this is basically a question of visualization. If an electron is not deflected, if it's not going to get deflected when it is passing through a certain region in space, can we certainly say that there is no magnetic field in that region? Is it really true or is it false? That is what we try to understand. Anybody? Is it true, children? If electron is not deflected when it's passing through a certain region in space, okay, no deflection, then can we be sure that there is no magnetic field? Can we conclude as there is no magnetic field? That there is no magnetic field? The answer here is actually no, you can't. Okay, no. Why? The electron could not be deflected if the velocity and magnetic field are going to be in the same direction. Okay, so here you need to understand that it is no, the electron would not be deflected. Okay, it would not be deflected if the velocity, that is how it is moving, and magnetic field are in same direction. So it all depends on the direction. Very important. Okay. So both of them are in same direction, then it cannot be deflected. You understand why? Why force F is equal to QVB sine theta? Both are in same direction. Theta is zero, sine zero, zero, no force. Is it clear? So this is how you try to understand, how you try to visualize the given situation, and then you make a fair conclusion out of it. That's the first visualization. Okay. Now we will go to the next one. What is the next possibility? The next visualization. Okay. This I will call it as one visualization one. This we will call it as I will call it visualization two. Okay. Say now if suppose okay, if a moving electron is deflected sideways, if a moving electron is deflected sideways on passing, say on passing through a certain region, on passing through a certain region of space, okay, can we be sure that magnetic field will be existing in that region? Okay, can we be sure of magnetic field existing in that region? Can we be sure of it? Is the question. That there is magnetic field that is existing in that region. Okay. So if a moving electron is going to be deflected sideways on passing through a certain region, can you be sure that magnetic field is existing in that region? Is the question. Okay. Now here you need to understand sideways deflection, whether it is going to be only due to magnetic field, not necessarily. Do you remember the Lorentz force I taught you in the last lecture? Isn't it? It can be possible even because of that. So sideways deflection may be due to electric field also. It is possible due to electric field also. In the absence of electric field, what can happen? The sideways deflection will show the presence of magnetic field. So here also the answer is no. Okay, it's no because it can be due to the deflection. Sideways deflection can be due to electric field also, not necessarily magnetic field all the time, because you have something called as Lorentz force, which takes into picture electric field also. So therefore, that is also one aspect that you will have to keep in mind. Okay, so here it is no sideways deflection can be due to electric field as well. Okay. So that also you must keep in mind. This is the second visualization. Okay, that's it. This is the second one. What are the other possibilities of your visualization? So these are the things which you will have to keep in mind whenever you want try to approach any questions. Okay. So third one, third visualization. If a charged particle at rest experiences no electromagnetic force, then is it compulsory that electric field will be zero? Again, is it so, or is it really true? So like this, you will have to try to visualize certain concepts and then come to a conclusion. Okay. So I've given you two visualizations. Okay. So just to keep in mind, now as we do problems also, we will try to visualize and come to a conclusion. It's not a big deal. Okay. So now we will go back to the questions. Okay. So I will try to project that questions part. Okay. Just give me a minute, children. Let me load that. I've started sharing it. So these were the questions, which I've shared, in the last class. Okay. So certain questions, I have shared it. So I hope positively some of you would have tried it. Certain questions you would have definitely got it. Certain questions. Now the concepts I've taught in this session. Okay. In today's session. So the first question, which is there on the screen. Okay. This is the first question. So you have an arrangement of three parallel, straight wires that are present, which are placed perpendicular to the plane of paper. So you can see the configuration here, A, B, and C. They have already marked. Okay. Now you can see because it is a dot representation, it's perpendicular to the plane of paper. Okay. And you know the dot represents the magnetic field that is going to be present outside. Okay. As per our analogy that we have learned. Now, the question is, what is the magnitude of force per unit length of a wire in the middle? Okay, in the middle portion. A, B, C is there. The distance between A, B is B. The distance between B, C is also D. And the angle between them is 90. That means they are perpendicular. AB part is perpendicular to BC. So all the information that we have. Okay, and the current is I through the wires. The current is same only. There is no change in current. Okay, this is what they have given. They are asking you what is the magnetic force per unit length on at the middle part. Okay, at the middle portion is what they are asking here. Okay, at this portion. So therefore, you know that there is force experienced at BC, there is a force experienced by AB also. There are two different aspects here. Okay, force experienced by BC is also there, a part of the wire. Here the wire is going to be experiencing a force, okay, and on that direction, FBC, there is a force. Same way the force also is going to be experienced by the wire at portion from B to A. Okay, because here you have another wire that is carrying current, so that wire also is going to experience force. So BA, these are two vectors. Okay, so whenever you have two vectors like this, can't you find out the resultant of these two vectors? Right, it's possible to find out which law we will apply to find out the resultant of these two vectors. Anybody? This you have already, you have already identified.
Triangle law, sir.
Yeah, triangle, or you can say parallelogram law. According to parallelogram law or triangle law, you know that if there are two vectors, say f1 and f2, the resultant of two vectors is under root of f1 square plus f2 square plus 2f1 f2 cos theta. And cos theta here it is 90. That term will go away, right? What happens to that corresponding term? Cos 90 becomes 0, right? Isn't it? Cos 0 is 1. So that term will go. So it is only under root of f1 square plus f2 square. That's it. So you substitute that, okay? And both the forces are, you can see it is at equidistant points, okay? So we can simply say, I'm coming, I'll show it to you on the screen, because both of them are at same distance, okay? So the force also will be experienced by both of them will also be same. So by resultant, or we say F net is equal to under root of FAB square plus FBC square. Okay. Actually, I've written as AB. I'll change it. Okay. From B towards A. So vector means direction. You have to be careful. So FBA the whole square plus FBC the whole square. Because both are equal in magnitude, the forces, because the directions are also equidistant. So we can simply write, in general I'm writing. So I can write as 2f square. Is it correct? So we can write it as 2f square. Now that f you can take it out of the root. So it will be root 2 into f. So this is the net force. Okay. Now they're asking you what is the force acting per unit length. F by L is what they're asking. So go and substitute. Okay. You remember I taught you the concept for force acting per unit length. If you go back to the notes and if you're going to see what is the force acting per unit length, you try to understand what relation. Can you tell me what is the answer here when you go to substitute? Just try it out. This question is simple only. Can you try and tell me what you're getting? Mu naught I into I dash, you remember? 2 pi into A. Use that relationship. Okay. So the current is same, I only. So I times I is going to be I square anyways. Isn't it? The force acting per unit length. So you try to use that, make use of that relationship. to make use of the that corresponding relationship. Simple. Okay. So what happens? The net force acting for unit length. So substitute the cases. Just go for a substitution and then you try to simplify it. You will get the answer. Just give it a try.
C, sir.
Answer is option C. Isn't it? Okay, we will see. So here again, root 2 into F. So force acting per unit length. Again, here I am going to substitute root 2 times F is nothing but, it is mu naught times I1, I2, I square only divided by 2 pi A. Instead of A, I am writing D. That's all. Okay, 2 you can write as root 2 into root 2. Simplify it. Finally, you will get mu naught I square upon root 2 pi into D. That's it. That is the answer. So which option is true? The option is C. Okay, the third option is correct. Okay, that is how you solve this question. Okay, it's a simple approach only. But you will have to understand that here resolution of vectors also comes into picture. Okay, I mean simplification of two vectors using the parallelogram or the triangle law. You use it and you find out. Okay, that's it. Second question. This is a simple one. A long wire carrying a steady current is bent in the form of a circle of one turn. If the magnetic field in the center of the loop is B, then it is bent into a circular coil of n turns. Okay. Then what is the magnetic field in the center of this coil having n turns? Is the question.
N, B, sir.
Yeah. What it will be? It will be n times B. Okay. Yes. Okay, so it is going to be n times B. Why it is n times B? Because n number of turns. No, magnetic field also will be enhanced by n times. Simple. Okay, that is why it becomes n times. That's it. Okay, so we say it is n times B. Good. Third question. You have a long straight wire of radius A, which is carrying a steady current I. The current is uniformly distributed over its cross section. They are asking you what is the ratio of magnetic fields B and B dash at radial distances of A by 2, that you are it is reduced by half. The second one, it is increased twice. Okay, from the axis of the wire. What will be the ratio of magnetic fields? B and B dash.
4, sir.
4. How did you get 4? Can you tell me? Correct. Tell me. For B and for B dash. B, it is corresponded to A by 2 distance, and for B dash, it is 2A. So what you have done? Which relationship have you used? Easy. What is the formula for magnetic field that you have used for a straight wire of radius A that is carrying current?
B not equal to, sir, B equal to not Ni by 2A, sir.
B is equal to mu naught and N. Is it NA or NI?
Ni by 2A, sir.
Yes, Ni upon 2A. Okay. So where A is nothing but radius, okay, or the distance. So you use this corresponding relation. Okay, mu naught, number of turns also you can see. Okay, but they are telling just it is going to be just a wire. So you take it. So what is the magnetic field experienced by it? For the first one, A, you will, in the place of A, you will put A by 2. For the second one, you will put 2A children. A will get cancelled, right? And 2 gets multiplied, and therefore you will get the answer. Okay, so go for a substitution and then go for a simplification. So substitute the values. So here you find out the ratio of B upon B dash. So what is there for B? You again substitute. So for B directly I am substituting. So you will get mu naught N into I upon 2 times A. So the first one they have told A by 2. So that goes up and it is going to get reciprocal. So appropriately that gets cancelled off. The second one you can see it is going to be 2A. So that also gets multiplied with the 2 which is present, and then it becomes 4. Okay. So, so substitute it. and then you go for the simplification part. Okay, so that you it gets reciprocal and you will get the answer. Fine. So that one I leave it to you. It's easy to solve. Moving on to the next one. Fourth question. You have a square loop ABCD that is carrying a current of I and it is placed near and it is coplanar with a long straight conductor XY carrying current I. So what is going to be the force, the next force on the loop? So let's try to picturize this. You have a square loop, say it is A, B, C, and D. This is square loop. It is carrying current of I, say the current is I through it. It is placed near and coplanar with a long straight current carrying conductor. So which is I. Okay, what is the next force experienced by this corresponding loop? That is the question. So you have to find out what is the force experienced by it. So what relationship can be used here to do it? I leave it to you. Which relation would be a perfect fit? Just think for a while and then you can.
And B, sir.
Okay, B. I'm asking you not the answer. What is the relation that you are using that you have used? It may be B. Okay.
Sir, force on a small conductor carrying wire due to infinite large current carrying conductor, sir.
Okay, due to an infinite large current carrying conductor. So, what is the relationship formula?
F equal to mu naught I dash L by 2 pi A.
Yes, mu naught I dash L upon 2 pi. So, we are using that corresponding relationship. Okay, so two currents. So, here first current is I, which is flowing through this. The second current is capital I. Okay, so I capital I and small I into length L upon 2 pi. So, making use of this corresponding relationship, so we can come to a conclusion. Here, this square, when there is a square loop, generally one part of the loop means easily we can find out, right? So here it is I and here also. By the time it comes here, it is downwards, isn't it? So therefore, when you have a square loop, what are the corresponding possibilities? Okay, so that is what you will have to think here. Okay, it's a square loop. So then when you try to find out what is going to be the force, next force on this loop, so you need to consider both the configurations. So it is at a distance of A only they have told. When they say it is at a distance of A, that means it is basically this length. They are not telling us the full length. So whenever you have questions like this, you need to understand. Now here we don't have information about the length of the square. Okay, length of the square, there is no information, and they have not represented that also as a variable. So therefore, whenever you have questions like this, you will only consider this as a straight current carrying conductor. Okay, you will consider that there is one long infinite conductor or a very long conductor, and there is another conductor which is short. Okay, whose length is known to us, say which is carrying a current of I. Simple, as simple as that. So therefore, considering like that only, you will proceed with this. That's the reason you will come to the nearest conclusion as option as B. So always go by the method of elimination. Whenever you try to see such questions, so you look at it, look at all the options. Which option is very close, to the relations that we have learned. Okay, that way you can conclude. Okay, next, moving on to the next question. You have a proton and an alpha particle. Both of them are entering. Now, what is a proton and what is an alpha particle? Okay, these are two different things. One is proton they are saying, one more they are telling it is an alpha particle. Are both same or both different? If it is same, how? Or if it is different, how is it different? Yes. Proton, everybody knows. I know proton is the basic thing, which you people would have learned definitely for sure. Okay. But what about your alpha particle? What is it? What is an alpha particle? Where have you come across this? Have you heard about this Rutherford's alpha particles scattering experiment? You would have definitely learned that, right? Basic structure of an atom. There, that alpha particle comes into picture, right? Isn't it? Stream from that the experiment conducted by Rutherford. He takes a lead block, which is a classic source of alpha particles. So alpha particle is basically it is also one small particle which is having a special charge. Okay, there is a nature for it. Okay, this is basically a helium nuclei. Please keep this in mind. Whenever I say alpha particle, I'm talking about a helium nuclei. Okay, a helium 4 nucleus is what I am talking about. Okay, whose mass is 4. 4 atomic mass units. So we are using that only. That is basically your alpha particle. So you take a proton and there is an alpha particle. Both of them are entering the region of uniform magnetic field, which is B. They are moving at right angles to the magnetic field B. So if the radius of the circular orbits for both the particles is equal and the kinetic energy acquired by the alpha particle is going to be, okay, is 1 mega electron volt. When we say mega electron volt, okay, it is basically, the energy, generally the energies in, for the atoms, we are expressing in terms of electron volts. Okay, when you say mega, it is quite big. Okay, so the magnitude is quite huge. Okay, that's it, children. So they are asking you the energy acquired by the alpha particle. What will be the corresponding energy acquired by it? So, any idea about this? Or you're hearing this for the first time?
Sir, to find the ratio between the kinetic energy of proton and alpha particle in the field, sir.
Hmm. Hmm. Kinetic energy. Okay. Kinetic energy, which relation you have used? Is it half mv square or something else? Because you don't have any information about the velocity. They're saying they're moving at right angles to the field, and you just have the information that both of the radius is also circular, and they are saying it is equal. The kinetic energy is given here in this question. What is the energy acquired by the alpha particle is what they are asking. Which formula can we use here? Any idea about the formula? They are talking about energy. So energy means what relationship can we use? This comes basically, in atomic physics. The atomic part it comes. Okay. So that is where it comes into picture. Fine. So here still we have not touched that part. So even if I'm going to tell you, this is going to be Greek and Latin. So when we do that nuclear physics part, so I'll definitely address this. So here you need to understand the relation between the kinetic energy of both your alpha particle and the proton. There is a small relationship, children. So we make use of that relationship. Okay. And we will be solving this particular relation, this question. Okay. So we will do it. That time we will do. Okay. So still we have not touched that part. It's an application of the atomic physics, nuclear part. So we will do it. Okay. Fine. This one I think you all know the answer for this. The sixth one. An electron moving with a circular orbit of radius r and it is making n rotations per second. Here you see, children, frequency indirectly they have given. Okay. So magnetic field produced the center. You remember I gave you the frequency relationship. So make use of that relationship. EVR by EVB by R. So that relationship you will make use of. So what will be the answer for this? This you can say directly itself.
Sir, zeros.
Okay. Yeah. Is it zero? Why zero? Somebody said zero. Why is it zero here in this case? Yes, children. Whenever you take a circular coil that is going to carry current, and here they have told that is N revolutions. Okay, simple. The formula that you will use, direct formula relationship. D is equal to mu naught I upon 2R. You make use of this relationship where I is nothing but the current that is going to be flowing in the coil, isn't it? So when you say one revolution, the number of revolutions, okay, is they are telling it is making n rotations per second. Okay, so time taken for say it is going to move for one revolution is going to be 1 upon n, isn't it? So you know all know that current I is equal to Q by T. Make use of that relationship. Okay, from current electricity, I is Q upon T. Here, what is Q? Electron. Electron means it is going to be E, isn't it? So E upon time. Time I am expressing in terms of this frequency also. So it is nothing but 1 by n, number of revolutions. So I am writing it as 1 by n. So go and substitute. Okay, n will get reciprocal. Okay, so what will be the final expression? You will get B is equal to mu naught Ne upon 2R. That's it. Okay, mu naught Ne by 2R. So answer is option B in this case. So please keep this in mind. Okay, whenever you approach such questions, try to use the formula. Here you are relating the current. Whenever there is an electron moving in an orbit, obviously there is going to be in magnetic field, definitely it is going to experience current. Phi is Q by T. You make use of this relationship, and then you are going to express it. Simple. In the place of I have put N. Okay, and then you go for expression. There is even one more way of approaching. In the place of you know the charge quantization relationship also. Okay, charge quantization relationship can also be appropriately used. Okay, because they are telling per second, so T time would go away. You will get in terms of any again. Fine. So that is how you approach this question. Sixth question. Fine. So like this, you do it, children. Again, here also they have given you the magnetic field in this question. You see, magnetic field is given as 2 into 10 power minus 4. A long straight wire is carrying at a perpendicular distance of 5 centimeter. An electron is also at a distance of 5 centimeters from the wire. It's moving with a velocity of 10 into 10 power 7 meters per second towards the wire, and it's perpendicular to it. Here you see it is perpendicular to it. Perpendicular means do you remember one long straight wire and one more short wire. Okay, the distance between them is A. I have taught this concept today. And one more wire of length L. So obviously it is going to experience a current. This wire will have a current, and this wire also is going to carry some current. So using that relationship, you have to solve this corresponding question. So that is how you will have to visualize, and you will have to do it. So if you're using that relationship, what would have been the answer for this? You have all the data here in this question. So if you're making use of that relation, what would be the answer? Just for a while you think. So what is the force, children? Force experience is going to be whenever you have a wire carrying current and it is experiencing current, and at a perpendicular distance of 5 centimeters from the wire, you have an electron. That means due to wire, there is a small electron that is revolving. So whenever you talk about that, it is nothing but force. Which force? The force due to the magnetic field that is going to be provided, because they have given you magnetic field here, right? And there is no electric field. So purely it is force due to magnetic field. So you apply that and you try to solve this question based on the given data. So always think based on the given data. FB is nothing but QVB sine theta, isn't it? Make use of this relation. So if you are going to use this relation, Q is nothing but electron charge. Electron charge 1.6 into 10 power minus 19 into velocity 10 power how much? 7. Okay. And they have given you magnetic field. How much is that? 2 into 10 power minus 4. Isn't it? That's all. Go for substitution and simplification. 10 power minus 19 minus 19 plus 7 minus 4. So I think you will get 10 power minus 16, isn't it? Into 3.2. So 3.2 into 10 power minus 16 newtons is the force. So the answer is option B in this case. Okay. So first we try to understand that there is a particle. It is not another wire. right? It's not two wires. One wire, obviously. One more is basically a particle. When you have a particle and the wire, formula to be used, F is equal to QVB sine theta. Force experienced by a particle due to a current carrying wire is this. Force experienced by a wire, short wire due to a long wire, that is different. Okay, so that way you will have to differentiate between the nature of the question that is being asked. Okay, so this is how you will approach and you will solve this question. Okay, particle means this due to a wire. Two wires, that's a different concept altogether. Okay, force acting per unit length, mu naught I1, I2, or mu naught I squared, if the current is going to be same upon 2 pi a. You remember that relation we will use. So based on that, you will have to wisely choose which formula would be a perfect fit for solving. Okay, we'll finish off this. So next you have the eighth question. Okay, circular coil is carrying a current of I, which is placed in uniform magnetic field. Okay, so what is the magnetic force? Okay, if the magnetic force on the segment is going to be F, AB is going to be F, then the force on the remaining segments, which is BC, DA. They are asking what would be the force experienced by the remaining segment. Okay, that is what they are asking. This is also easy only. So whenever you have a circular coil that is going to carry current, okay, on the remaining segment BCDA, try to space, underline that particular part. Where is that BCDA part? This is BCDA. Okay, BCDA part, remaining segment part, we try to find out. Okay, so what will be the corresponding force? Now, force due to AB, this part, this portion, force due to AB, okay, there is a current that it is going to carry, okay, and it is present, it is placed in uniform magnetic field. That is what they tell you. So on AB, if it is going to be F, what is going to be on BCDA? That is the remaining segment. You need to understand that the current that is flowing is going to be same. The current will not change as it goes through the other parts. Circular loop that is carrying current. Okay, that is going to be uniform. Current does not change. Okay, the direction changes, of course. Therefore, you need to understand by the time it comes from B to C and then it goes to A, right? B, C, D, and it is A, it is going to go upwards. Here it comes downwards. So we need to understand that the total force experienced by a current carrying loop is going to be zero. The force due to AB and due to BCDA is going to be zero. Net force is zero, right? We make use of this relationship. Due to AB, we all know that the force due to AB, as per the question, is given as F. This is F. So F plus force due to BCDA is zero. So what is BCDA? The F term goes that side, it becomes minus F, right? The answer is minus F. So it is minus F. Option A is right in this case. Okay. So again, you need to understand the concept that the net force experienced by a loop which is carrying current of I amperes is going to be zero because the current traverses all around the loop and comes back to the original point. So it is going to be zero. That's it. Due to the portions in the wire. Okay. So that's how we approach this particular question. Fine. So like this you can do it, children. Next question also I think you can do it. Two similar coils are lying concentrically with the planes at right angle to each other. The current flowing through them are I and 2I. They are given. So then what is the resultant magnetic field at the center of this coil? Two concentric coil circular coils is what they are given. Okay. So appropriately for this also, children, you can find out. So again you make use of the relationship and you can get the answer for this also. What will be the answer for this? When you have two like coils of radius r, now then they are carrying currents of I and 2I. Okay, which option would be true for us? I mean, in this case, A, B, C, or D. Just go by the method of elimination. Look at the options very closely. Okay. The general formula. What is the general formula that we use? I'll just give you an idea. B is equal to mu naught I upon 2R is the general formula for a loop that is going to carry current. Right? Now they have given you two different loops. Okay. So the magnetic field due to the loop 1 and loop 2. When they are saying the loops are at right angles, the way the loops are being drawn, you will take one loop like this, the second loop is like this. Only then they are going to meet right angles like this with respect to the radius of both the loops. Okay. So one is carrying a current, say this loop is carrying a current of I and say this loop is carrying a current of 2I. Then this is going to be the case for both the loops. Okay. So you have to find out what is the magnetic field. So for the first one it is I. For the second loop, say this is first one children, B1. Say for B2 for the second loop, the formula will be magnetic field mu is equal to mu naught. This time not I, it will be 2I divided by 2R. Okay. And what is the net magnetic field? Again, parallelogram law you will use. Are you understanding? Magnetic field. So you will use parallelogram law. Again, you can see between both, you can see the angle is 90 degrees. So what will you do? The net magnetic field will be equal to under root of B1 square plus B2 square. That's it. So you will apply it and go for the simplification. Substitute it. When I substitute the relation, what do I get? So under root of B1 square. B1 is mu naught I upon 2R the whole square. Wherein for B2 is mu naught 2I. The 2 we can cancel, right? So we can simply write it as mu naught times I upon R the whole square. So we can express it like this. Okay. Take all the possible common outs. All possible common out terms you try to extract and then you try to express it. Okay. That's it. So when you take the possible common out terms and you extract, you will get mu naught I upon 2R itself. If I take it as common out, inside I will get under root of 1 square plus there you have a 2 terms. See, those 2 squares. 2 square is 4 plus 1 is 5. So root 5 times mu naught I upon 2R. So the answer is mu naught root 5 mu naught I upon 2R option C. So like this you will solve. So based on the question, frame the figure, draw the figure, try to illustrate, and then you go for a solving approach. Okay, for this you will have to learn the formulas. First formulas should be in your fingertips. Once it is in your fingertips, then you can start solving such questions with ease. Okay, that is how you can approach these type of questions. Okay, so with this we'll wind up. So